In this problem, we are concerned with freeform motion. A coin is dropped from the roof of a building and falls freely from rest. What are its position and velocity after 1 second, 2 seconds, and 3 seconds? So once again, we will solve this problem using the kinematic equations of motion and also using the velocity time graph. And the first step is always to create our reference frame. So in this case, let's say this is the building. Then our reference frame is attached to the roof of the building, the top of the building, and the positive direction is pointing downwards. Alright, so in this case, because this coin is dropped from the top of the building, from rest, so our y0 is equal to 0 meters, because our origin is attached to the top of the building. And our v0 is equal to 0 meters per second because the coin is dropped from rest. And our acceleration a is simply equal to g because our positive direction is pointing downwards, which is equal to 9.8 meters per second squared. And once again, we choose our t0 to be 0 seconds, meaning that we start our clock when the motion starts. So this will be the data for our current problem. First, we are supposed to find the position at t equal to 1 second. And in this case, we simply use the equation of motion, y is equal to y0 plus v0 t minus t0 plus half a t minus t0 squared. And our y0 is from here is 0, and t0 is all 0 here, and we also don't have v0, so this term here is 0. But we do have our acceleration, which is 9.8, so plus half 9.8 t squared. Alright, and for the velocity, we have v equal to v0 plus a t minus t0, which gives us 0 plus a is 9.8 t. Okay, so with these two equations, we can generate the position and the velocity at the 3 different times. So for part A at t equal to 1 second, our y is simply equal to 4.9. 9.8 divided by 2 is 4.9. T squared is 1 squared, so this will give us 4.9 meters. For the velocity, v is equal to 9.8 times 1, which is just 9.8 meters per second. At t equal 2.0 seconds, y is equal to 4.9 2 squared, which is equal to around 20 meters, and v is equal to 9.8 times 2, and this is also 20 meters per second. Finally, at t equal to 3.0 seconds, y is equal to 2.9 times 3 squared, which is around 44 meters. And our velocity v is equal to 9.8 times 3, which is around 29 meters per second. So we are able to easily solve for the position and velocity at the 3 different times using the equations of motion. Okay, and that is pretty straightforward. Let's move on to the graphical methods using the velocity time graph. So using graphical method, the first step is of course to sketch out the velocity time graph. So the vertical axis represents the velocity, and once again the horizontal axis will be the time axis. in seconds. And in this case, because our acceleration A is equal to g, it is positive, so we have a positive slope here, which means we have a straight line. Alright, and we are supposed to find out the velocity and the position at 1 second, 2 seconds, and 3 seconds. So say this 1, this 2, and this is 3. Alright, so the corresponding velocity will be this v1, v2, and v3, v sub 3. So in this case, for v1, let's say, the displacement at t equal to 1 second would be the area under the vt graph, right? We know that from our past two problems. Okay, so our task is to find out exactly what is v1, what is the value of v1, the velocity, and also this area under the vt graph from 0 to 1. Okay, so for v1, since acceleration is delta v over delta t, this implies that delta v is equal to a delta t, so that v1 minus 0 is equal to 9.8 1 second minus 0, so that v1 is equal to 9.8 meters per second. Alright, so we solve for v1 using the simple fact that the slope is equal to the acceleration of free fall. Now to find out this area here is also very simple, because the area under the graph is actually the displacement. So we argue it this way: since velocity is dy over dt, alright, so dy, integration of dy is equal to integration of v dt, and let's put in the limits. This from y0 to y1, or the velocity here will be from t0 to t1. Right, so that we have y1 minus y0 is equal to, now this term here is simply this red area here, okay, which is the area of a triangle, which is half base times height, which is 4.9. This means that y1 is equal to 4.9 meters, right? Because y0 is 0. Okay, so we proceed in a likewise manner to solve for v2 and v3 and the corresponding positions as well, using the area under the graph. Okay, so now for v2, okay, the position would be this area here. Alright, okay, so this area of course is bigger than the previous area for v1, right? Now do not be mistaken, the area is not this area, right? It is not simply this orange color area here, right? It is not, okay? The area is the entire area of the triangle, the big triangle here. Okay, because we are talking about the position of the coin at t equal to 2 seconds, which means that from the time it has been released until 2 seconds, how much displacement was covered, which is this big area here. Okay, so let's proceed to solve for y2 and v2. So to solve for v2, right, we make use of similar triangles, because this the figure here reminds us that all these three triangles, this triangle, small triangle here, this bigger triangle from 0 to 2, and this, the largest triangle from 0 to 3, these are all similar triangles. So we can make use of the concept of similar triangles to help us to solve for velocity and the position. Okay, let's see how we do it. So for v2, we know that v2 over v1 is equal to t2 over t1. 1. Okay, so from this figure, V2 is this referring to this length here, V1 is referring to this length here. Okay, T2 is referring to this length here, and T1 is referring to this length here. Okay, so this is the formula for similar triangles. We have these two triangles, the big triangle here from 0 to 2, and the smaller triangle from 0 to 1. So this is the formula from the concept of similar triangles. So that V2 is equal to T2 over T1 times V1, which is 2 over 1 times 9.8. So that we have 20 meters per second. Okay, that is V2. What about Y2? For Y2, we can easily compute the area of the triangle. You know that delta Y2, which is the displacement from Y0 to Y2, is equal to the area of the triangle. Right, area of the triangle. We are referring to this big triangle here from 0 to 2. So this implies that Y2 is equal to half times base times height, which is around 20 meters. Right. We proceed likewise for V3. So from similar triangles, V3 over V1 is equal to T3 over T1. From the figure, V3 is referring to this length here, and V1 is this smaller length here. T3 is this length here from 0 to 3, and of course T1 will be this length here. So proceed to compute V3. V3 is then equal to T3 over T1 times V1, which is 3 over 1 times 9.8, which gives us 29 meters per second. So once again for delta Y3, which is equal to Y3 minus Y0, this is equal to area of the triangle. Area of the triangle, we are referring to this area of the big triangle here, okay, from 0 to 3, which is equal to half base times height, half 3 times 29. That will give us Y3 equal to 44 meters, because Y0 is 0 in this case. Okay, so we have come to the end of the solution process, and once again to recap, we have solved this problem on a simple free-form motion from the top of a building using both the equations of motion, right, and also using the graphical method. And in this graphical method, we have employed the similar triangle method to solve for the velocities, as well as using the concept of the slope of the graph being the acceleration, and also the area under the curve as the displacement. Okay, thanks for watching this video. I will see you in our next video.